Well, hello everyone, and welcome to this month's edition of Tech Talk. I had a little bit of trouble coming up with my topic for this month. It was kind of a hard road to hoe, and but at any rate, it took about 6 or 7 different turns as we're going through it to figure out what I wanted to talk about. And here we ended up talking about counters. And I thought, well, you know, everybody knows where counters are in their wireless system. They know, you know, where the numbers are, but may not know what the numbers mean, nor do you maybe know how those numbers are generated. So we're going to talk about counters from a slightly different perspective, a system perspective today. All right. So the agenda. Counters, why do we need them? We're going to spend lots of time on that. And what are they telling us? We're going to spend a little bit of time on that. What are the most important, and examples and some analysis at the end, very short about that. But we're going to spend our time talking about why we need them and what they're telling us. So let's review the OSI model. When we're dealing with broadband wireless, we're really dealing with 2 different subsystems, right? We're dealing with an Ethernet subsystem that connects to it, whether that Ethernet system is fiber or it's Cat5. Yeah, nevertheless, we have an Ethernet subsystem that's connected to it. The radio system is the second system that we're talking about because we have to get the signal over the air here. So the Ethernet subsystem includes what I would consider to be layer 1 and layer 2 of this model here, layer 1, layer 2, layer 3, because we're talking about IP, and we're also talking about segments. We're talking about end-to-end connectivity. Then at that point, the system changes slightly as we get over the air. Over the air, as far as this OSI model is concerned, we are mostly concerned with layer 1 here, the physical layer. But we also have some formatting that goes on, and so we have some of the MAC layer that is transmitted over the air as well. So we have layer 2 action over the air dealing with broadband wireless. So the thing to note, and I think that escapes us a lot of the times, maybe, is the fact that telecom is digital and analog at the same time. Every connection in a modern telecom system has a digital analog conversion or an analog to digital conversion. We have digital signal processing that goes on. When we can take and format the Ethernet frame, we can take and analyze the data in the frame. We can look and see what our QoS level needs to be, that sort of thing. We can take and manipulate that frame from a digital perspective in 1,000 different ways. In an analog processing, we're going to talk about our modulation, our transmission, our receiving, and our demodulating. So the thing to remember here is that while we're digital processing, we can store, we can remember a particular state, we can analyze, we can calculate, and we can adapt in near real time. Processors today are fast enough that frames come in, frames are analyzed, and frames go out, and we're talking about milliseconds of delay that's caused by the processing of the frame. Once we become analog and we go from a transmitter towards a receiver, analog can't store anything. Analog only transmits or receives, and it processes in real time. So we have these 2 conundrums where we've got the digital world that's that's connected to our analog world, and we have this junction that occurs many times within a telecom signal chain, as we'll see in a minute. All right, so let's talk about Ethernet for a minute. Most people don't consider the analog portion of Ethernet, but it is very, very important. in an Ethernet system, we have a digital interface, which drives what's called a hybrid, which converts the digital signal into an analog signal. The analog signal is then sent down the twisted pair, and this twisted pair then delivers that to a receiver, which is then converted back to digital, and off it goes, and we process it in the next device, whatever it is that we're doing. So every time that we reach the twisted pair, we have gone from digital to analog. And this is a 1000 base topology here in this little graphic. So the way that that gig E is brought together is that it's multiplexed 250 megabits per pair. We have 4 pairs, and so altogether we have the potential of 1000 megabits per second going across this this system. So we have in fast Ethernet and in 10 base T Ethernet, we of course are only using 2 pair. In 2 pair are idle, and but in 1000 base T here or in GigE, we're using all 4 pair. Now, just as a oh, by the way, I thought I would include this little drawing here also of how power over Ethernet is actually delivered from a power supply to an end device of some sort. So over our 4 pair that we have the analog AC information going over, at the same time we multiplex DC onto it. They use as the hybrid here, they're using a transformer, a center tap transformer. And if you follow this circuit carefully, what you see is that the positive goes to 2 pairs and the negative goes to 2 pairs, and it's fed at the center tap so that both conductors of the twisted pair carry the current over to the other device, and then at the other device it runs through a pair of bridges, and then to a power divider or a regulator, and then into a DC to DC converter right here, so that we can make use of whatever that voltage is. So in some cases it's 56 volts, some cases 48 volts, some cases 30 volts. And through this power divider and DC to DC converter, we can create any voltage that we want, +5, ±12, whatever it happens to be in the device that we're feeding the power to, and away we go. So with this, because of this analog connection that we have between the devices over the Ethernet, we can take and multiplex DC onto the AC that's flowing across the analog alternating current that's flowing across this at this particular bit rate, and we can take and pass DC over AC. If you notice here with the pin numbers, 1, 2, 3, and 6 are the opposite polarities here. So if I'm not using GigE, if I switch down to fast Ethernet, then 1, 2, 3, and 6 here are used for the Ethernet connection. When I'm in GigE mode, then of course I have 4, 5, 7, and 8 also involved in that, and altogether all 4 pairs bring up and constitute the GigE connection that I have between the 2 devices. This is why is this important? Because this is just a common circuit, a common connection between 2 devices that shows very clearly how we go from digital, analog on the connection over the cable, back to digital again. And so when we want to analyze the efficiency of this process, for example, we have to take and employ counters here at the digital section here. Easiest to do there. I can count the frames in, I can count the frames out of a particular interface, and I can see how many discards have been thrown away. So I've got all of that information that would be available on either side of this link. And so depending on the quality of the equipment and what we're doing with it, we can oftentimes we can see that. If this is a switch, for example, that's connecting to another switch, well, then of course we've got very detailed statistics about frames thrown away. We've got frames that are the number of frames that are transmitted across, how many bytes or bits there were in the frames, depending again on the switch manufacturer, and all kinds of information that we have here. Finally, in this last table here, just as a FYI, I've summarized what the different categories of unshielded twisted pair are and what their maximum lengths are, and so we can see here that if you want to take a screenshot of that, then you got the basics of the category, the UTP categories, all in one little table. So, Ethernet, digital, analog, digital. What's next? Well, now let's talk about radio. So in radio, lo and behold, we have exactly the same situation. We have a baseband, which is digital. We have conversion, a modulation conversion, and then we amplify it and we send it out to an antenna. Then it's called passband at that point. So baseband becomes, baseband is digital, passband is analog RF over the air. It's then received at the other end, was supposed to filtered. These are a graphic of filters, and then we undo the modulation process and turn it back into baseband again. So if we were to do this, why are we going through this little exercise here? Well, there's a few reasons. First of all, if we were to transmit pure digital information from baseband to radio transmitter and back to baseband again in pure digital format over the air, we would take a huge amount of spectrum to transmit a very small amount of data. Square waves, if we're going to take and turn an RF carrier on and off at some kind of speed that we could take and achieve, a decent data rate over the air, we would have not only the fundamental frequency of the square wave, but at the corners of a square wave. So if I have a square wave like this, at these corners, I am generating intermods like crazy. I will take, and at that point, I will generate first, third, fifth, seventh, ninth order intermods. All kinds of extra frequencies get generated as the carrier turns on and as it turns back off again. So pure digital over the air is a very inefficient way to transmit and receive the data. So what do? So RF is processed much more efficiently as analog. So what we do is we take and convert through a modulator, and we generate a carrier, and then we modulate that carrier, and then we amplify the carrier, bring it up to some kind of power level, apply it to an antenna, and send it over the air. Then a receiver some distance away can pick that up and reverse the process. So in analog, I can take and represent a large bit stream with a few symbols of over the air. We're going to talk about symbols here just in a little minute, just in passing. But I can represent a large amount of digital data with a fairly small amount of analog data over the air. And so this is why we do that. We want to conserve spectrum. Spectrum is the most precious bandwidth that we as RF consumers, if I want to call us that, that's our most precious resource. If we can make the most efficient use out of that spectrum, then we are going to have some happy customers on that we're delivering services to. So typically, anything from 1 or 2 bits per symbol up to as many as 20 or 40 bits per symbol is the state of the art today. So we can pass a lot of digital information over the air over a very little bit of spectrum. This is the deal. Also, one more thing is that when I have my square wave like this, if I were to pass pure digital RF over the air, so I have RF on, RF off here in this case, my power level over the air is 0, then my power level is full, and then my power level again is 0. And so this signal over noise then becomes a wildly infinite number. Pure digital is nearly infinite, so it's an impossible amount of power that would be required to go from a very short distance. Whereas in analog, the signal over noise can be managed in much more efficient way, and so I can get a farther distance with analog than I can with digital over with passing the same amount of data. So this is why we're gonna be analog over the air and digital on either end of that. So we have this baseband processing, passband processing, baseband again. So we end up at digital, but we get there in through this transition through analog. So you can see where I'm going with this, right? I think. Baseband typically are handled by integrated circuits today called DSPs, digital signal processors. Passband are handled by application-specific integrated circuits. That's what ASIC stands for. So in radio systems today, we have both. We have DSPs that are handling the Ethernet. We have handling the data, buffering, and all the other things that need to happen to it, storing it, and then it's handed off to a application-specific integrated circuit that has the modulators, transmitters, amplifiers, and all manner of other devices that are built into the integrated circuit, and off they go. So they're very powerful devices. The DSP and the ASIC is today. All right. So now that I've broached the subject of modulation just a little bit, another FYI. This was a rabbit hole that I went down that I didn't know whether I should talk about today or not. But in talking with a few of my friends over the last couple of weeks, the whole process of modulation can sometimes be a little bit of a mystery, especially in our broadband world. We're using what's called quadrature amplitude modulation for everything. BPSK and QPSK are forms of 2 QAM. This is 2 QAM. Right here is 2 QAM. Whoops. And this is 4 QAM, to name it differently. Then we have 16 QAM. We have 64 QAM, and we have 256 QAM, and on we go upwards to 4096 QAM in some of the very high-end point-to-point radios. So how does this work? So when I make my change from analog to digital, what I do is I split my data into 2 portions. So we can see here that I have 2 level shifters. When data, if data were to be presented, let's say 0010 was presented to my circuit here. When I split them, 00 would go to 1 level shifter, 10 would go to a 2nd level shifter, and then what this does is comes out with actually a DC voltage. So 00 would be here, 10 would be here. This DC voltage is applied to the modulator, which these 2 streams are 90 degrees apart from each other, and the sum of these ends up being one of the points of the constellation. So this 4-step modulation gets modulated into 16 QAM. So I have a 4x4 matrix here. So there it is. There's my 4x4 matrix, and so I have 16 discrete phase and amplitude points, I guess, that are created. I don't know what else to call them, but we'll call them points here since they're on here. And so my 0010 happens to be generated right there. So I have a negative amplitude and I have a positive phase, and away I go. And so I transmit the carrier in this state over the air for a certain number of microseconds. That is called a symbol. So in the case of LTE, this would be about 100 microseconds for LTE. For other systems like Cambium's 450, it's going to be a shorter time than that. For some Wi-Fi systems, it's even shorter than that. And there's all manner of different ways of doing this. But anyway, that's the essence of quadrature amplitude modulation. Now, when I have an OFDM system like I'm showing down here, I've got these carriers that I'm going to transmit. I'm going to have one of these steps for every one of these carriers. So I am going to generate a slightly different frequency on every one of these carriers so that I fill up my transmit passband on every one of these carriers. I'm going to modulate them with data that I've got stored, my DSP stores when it receives from the outside world, and I'm going to send it on to the other side. So if you're ever wondering about why the power consumption of a modern base station is as high as it is, it's because this ASIC and these DSPs that are actually doing this work, the digital part of the process and then the analog part of this process. If I'm doing a 512 carrier OFDM like the 450s, for example, well, then I have some number, 436 or some number of these stages in the ASIC that I need to process data at the same time so that this is transmitted simultaneously. These carriers OFDM carriers are transmitted all at the same time. They're not transmitted sequentially. So I'm not using one circuit to make all of these, to generate all of these carriers. I'm doing it simultaneously. So this is the beauty of a modern system. Again, because this is analog over the air, I can represent some bits with one symbol, and then I can take and generate a carrier, modify the carrier so that it represents that symbol, transmit it to the other end, and lo and behold, if I have a high enough quality signal, I can take it apart and put those bits back together again on the other side. This is in essence the process that I need to go through, and I need to be able to monitor this process. So we use counters for that. All right. Now, just from another perspective of the RF over the air, I'm going to send a bit stream that looks like this over the air. So when I go through the modulation process and I lay the bits in my constellation, this is what I end up with. So I end up with these being transmitted on various carriers, or if it's serial, if it's one carrier, I'm going to take and have these transmitted one at a time. They will be on the air for, like I said, a few microseconds, maybe tens, maybe hundreds of microseconds. And then I will switch to the next one, whatever the data is, in whatever order I want to transmit it over the air. The essence of scrambling occurs when I can take and mix this all up and then unscramble it at the other end and come up with the same bit stream again. But the trick in all of this is that I transmit a constellation that's really clean and crisp like this. When I get to my receiver, this constellation that looks like this when I transmit now looks like this kind of schmoz. So I have noise, I have propagation loss, attenuation, I have multipath, I have all sorts of RF conditions that are going to cause my constellation to not be very clear at the other end. And so getting this bit stream out of this received constellation requires a bit of processing in the, so this takes some processing to get this done. How's that done? Well, first of all, we use something called forward error correction here. 1 or 2 or 3 of the bits that are sent over the air, depending on what our modulation level is, may be used to generate a checksum for our forward error correction. So the transmitter knows what the data coming in is, multiplies it by the key, and then the difference, or the divisor, actually it's divided by the key, and then the modulus is sent to the other end. This end knows how to do the same math on it again. So it sees this constellation and takes a guess, really, at what it's supposed to be. Then the first step is it uses the forward error correction to be able to define that, what 4 bits in the constellation, if this were QAM 16, happens to actually be, and then ultimately comes out with the correct data. The data that was input becomes the data that's output. Now, if this isn't the case, if forward error correction can't look after this, then we have a couple of choices as to what to do. The first one is retransmit. So in almost every broadband wireless system today, there's a retransmit mechanism. So again, we have a conversion from digital to analog to digital. Then if a retransmission occurs, there's some feedback that goes back the other way, which is digital, analog, digital. Then the DSPs at the other end say, oh, okay, I'll retransmit it again. And we have the same process that goes over. So this digital analog to digital process is everywhere in telecom, absolutely everywhere. Now here's something that we don't consider either. So we're talking about fiber optics at this very moment. So a fiber optic channel is in fact above the RF spectrum. So, but it's still a wave that has a particular frequency, particular wavelength, and has a particular bandwidth. So in fiber optics, we're talking about a fiber optic channel having about 50 gigahertz of bandwidth. Current technology today, about 4 terahertz of total bandwidth is available in a fiber optic cable. And so we can pass, last month we talked about Shannon's theorem. So if we applied Shannon's theorem to this, the numbers that we could come up with would be spectacular in data going across this 4 terahertz bandwidth. How do we do that? How do we get it there? Well, guess what? Does this look familiar? Right here. Sure does. So what we have here is we have a case of digital signal processing in our media converter. Maybe we've got analog here coming in from Ethernet, but then we've got digital here. So we've got analog here. We've got digital here. Then we've got analog here, except the analog now is laser, and so our analog goes over the system, and then we're back to digital. Our Ethernet cable leaving is again back to analog, and then our switch or device, whatever we arrive at, we're digital again. So, look at that. It's the same kind of system, except that now we're just talking about much different bandwidth. So why do we modulate? Why do we go to analog in here? Well, it happens to be some of the same reasons that we do it in radio and we do it in Ethernet, is that I want to take and represent a string of data, some number of bits of data, with my light being in a particular state. Now I can take my laser and I can modulate my laser with the same phase and amplitude, my I and Q axis here, that I would with in a radio or in the Ethernet cable. So I can take and represent 2 bits or 4 bits per symbol on there. So I'm in fact I can use a less expensive, slower laser transmitter and receiver and pass a large amount of data over it. And we've seen technology in the past while go from gigabit over multimode fiber to 2.5 gigabits over multimode fiber up to 10 and more gigabits over that multimode fiber. And it's the reason that is happening here now is that is as our laser speed comes up slightly, then we can modulate it and pass more data over the air. So we still have this same situation. We have a case of digital to analog all the way along here. And I've shown here, just as an FYI, the in wireless here, this is going to become kind of the new standard of SFP. And so typically in an SFP we have one transmit and receive pair of fibers. We have an LC connector or something like that that connects in, and away we go. The latest and greatest is going to be multiples. So here in this case, I'm showing you an SFP that actually has four fiber pairs, transmit and receive to the other end. So now I take my bandwidth, whatever it is that I'm generating here, and I multiply it by 4 over this same system. So now, you know, and who knows where the end of this is, right? It's huge. So because of the need to fit a lot of data into a smaller bit of bandwidth that we can manage with less expensive components, then we do this digital analog and back to digital conversion again. This is kind of the reason for this. All right. So let's take a look at a typical broadband wireless system. I use the Telrad base station here for those of you who recognize it, just because it's got the antenna is separate from the radio, but it's all together in one piece. So the manufacturer or the type of equipment doesn't matter. This process is the same right across any brand, and really any kind of modern fixed wireless or system that we have out today. So we have some kind of network stack, right? We have switches or routers or whatever this happens to be, and it's digital processed inside. And then as we send our data towards the radio, it's digital here, right? We convert it to analog. In this case, I'm going to show a twisted pair, but this could be fiber as well. It doesn't make any difference. It's analog, and then when it arrives back at the radio again, we're now digital again. Then we modulate it, and we go through the whole process with the ASICs. We turn it back to analog, so we're over the air, we're analog, and then we get to the CPE, and we process. We process the signal, and that's digital, and then we send it over to the customer, and that's analog again. And then finally it arrives at the customer, and the analog Ethernet is converted back into digital, and in there, in this case I'm showing a laptop, it becomes baseband again. So here we are. This is the way to look at it, is that we're baseband, then we go to passband over the connection medium, then we convert back to baseband inside the radio. We process all the data, and then we convert it back to analog over the air analog, and then so it's passband at that point. Then we hit the CPE, we become baseband, come out of the CPE with Cat5 or with fiber optics, whatever it happens to be. And fiber optics are coming in the future. CN Wave, for example, out of the V3000 could be fiber optics. So we have CPE devices that are fiber optic connected, and then into customer equipment, and away we go. And we process it digital. And then if I wanted to extend this out, we have digital to analog conversions all over the place, right? As we deliver the data to wherever it needs to go. Same thing in the reverse, in the uplink, in the transmit direction from the customer or from the subscriber. We have exactly the same process. So we need to know at each one of these junctions right here, inside here, inside of here, and inside of here, what the performance is that we're seeing. So in every time that we convert from digital to analog, or back again to digital, we need to be able to see at that point how many frames or how much data is transmitted, how much data is errored, how much data is received, how much data is discarded, and how much data is malformed, maybe with errors, and from that maybe we can see how much data is corrected by the forward error correction, that sort of thing. So we need to see that all along the way. So today in our modern telecom world, we have counters. We use the counters. So here's the typical Ethernet counters on my 450 from my lab. Off of the Ethernet interface, we can see that I've got in octets. I've got in octets, I've got in packets, and I've got counts of, what is that? I can't read that word. My eyes are tired today. Yike. Anyway, I've got packets that packets and converted to octets to bytes that I can see in both the in direction and the out direction from that interface. This is the minimum that we need to see all the time. Because this is in my lab, my connections are all really, really good. So I have no CRC errors. I have no receive overruns. We can by the title of the counter, we can often determine exactly what that counter is going to generate. So CRC errors, very simply, that's the forward error correction. Do we have errors? No. In this case, I don't. Receive overruns. When I have that cloud of receive constellation, did the receiver take and make one bit into two or more? Do I have more bits in my frame than ought to be in the frame? So that would be called an overrun if that were the case. Do I have a frame coming late? Do I have a reflection or multipath in my analog path? That would be late. Do I have a transmit underrun? Has my DSP let me down and not filled the frame to the size that it's supposed to be? All of these, and I could spend hours talking about, the details of what each of these counters do, but they're all important. And so they will tell us things about what's going on if we have errors in the off of this particular interface in this case. So I have all right. Let me go to the radio now. So I took and I'm looking at the counters then on the other side now, my RF interface. And so in the case of Cambium stuff here, look I've got the same values. I've got in octets, unicast packets and non-unicast packets. That was what that term was that I couldn't read. And so unicast and non-unicast packets, so I can see what my distribution of packets in and out of the interface. This is out of the receiver now. This is into the transmitter and out of the receiver in this particular case. So I have a number of bytes. I have a number of out unicast packets. I have a number of out non-unicast packets, and I have a number of out discards that for whatever reason over the air, there's been errors, there's been retransmissions, whatever the case happens to be, and these frames were thrown away because they were damaged in some sort. So from this, I can form up percentages. I can see how many packets were discarded compared to how many packets were received, for example. And this percentage is very, very low. So as long as I'm in the 1-2% kind of range, then my system is probably okay. And so each manufacturer will take and display this in a certain way, but nevertheless, the information is exactly the same. What I'm looking for is I'm looking for what I'm transmitting, and then I look for the receiver at the other end. Now, in this particular case, I would go to a subscriber module and I would look at the statistics in the subscriber module, which would be exactly the opposite on the radio as what I have here at the access point. And so I could compare then to what performance I see there to what performance I have here. And theoretically, if I added up all of the frames that were received by all the CPE connected to an access point, I should come up with numbers that emulate the numbers that are right here. This is one of the ways. If you've been on courses that I've taught before, LTE courses or really any radio course, I talk about verifying the operation of the radio, and this is one of the ways to do that. So now in LTE, we have very much the same situation. We've got counters that are talking about our over-the-air transmit. I didn't show the Ethernet counters here because they are the same as what I've shown already in the Cambium system. But in LTE, we have this whole business of creating the resource blocks. So that means that our counter values are a little bit different. We're looking for slightly different information. Then we're looking for first of all our received signal strength right here. We're looking for our performance, our link quality, our signal to noise ratio right there, and we're looking for the downlink and uplink block level error rates that we see here. So in this case, I've got this one CPE is actually receiving a lot of errors and probably causing lots of retransmissions. And I imagine if I did a link test over it, comparing let's say the 12,000 here to the 9,000 here, I would probably see a huge difference in the performance. We can see it in the modulation level. So in this particular case, I've got this downlink bit level error rate, this percentage, and so it equals a lower modulation level. So my modulation level on my 12,000 is not perfect, but there it is. I can see how efficient I'm being over the air. And the same thing in the uplink. In this case, my uplink is not very good, a little bit better, and pretty spectacular in order. And we can see that when we look at the uplink RSSI, that I see that difference right here. So my counters are telling me, if this were a live working system, my counters are telling me that I've got a problem with the CPE 12,000 and the CPE 9,000. I have a different problem with my CPE 8100, but nevertheless, I read that from here. I don't have to go to the CPE. I don't have to log into it or anything to see that. The counters that the network tells me will, in fact, inform me as to what's going on here. So I need to use these to be able to identify what's going on. If I know the theory of how these values are put together, what the processes are, then the values become meaningful to me. Once upon a time, I was in about 2008 or so, I was teaching an RF course on some WiMAX stuff. And one of the students in the class accused me of being able to see the RF because I was describing it as though it were a person, it were the system as we're a living thing. And I thought about it for a minute, and I thought, well, that was quite a compliment actually. And it was good that we treat things as a system and every network as a living thing, because then we can take and understand exactly what's going on, exactly what changes. And then some things that we don't understand we can take and there's lots of material out there, lots of literature out there that will take and describe these processes. And some of it's pretty detailed and some of it's pretty deep and actually hard to understand, but there's always guys like me out there who can take and break this down into something that's a little bit simpler and give you the 311 on what's actually going on with you know, any kind of system like this. So that's my little introduction to counters. We're gonna talk about monitoring networks and how to do these things very much over the next few months. This month, I was scheduled to have one of the engineers from Pre-Seam on my on Tech Talk, but with WISP America on this particular month, he's very busy, and so we'll have to schedule that for the future. But that's going to be very interesting. It's going to tie into very much what we talked about last month and what we talk about this month. So as we go along here, we're going to keep digging a little bit deeper into the operation of broadband radios and their connected network devices. We'll see what happens. We'll see where we go next. So anyway, I really appreciate you taking the time to watch, listen to the video, and join the conversation. Love you to send any feedback to marketing@mbsiwave.com right here. Any suggestions for topics that you want to see? Again, marketing@mbsiwave.com, and between Nicole and I, we'll sort through the email, and I will venture into the topics that you suggest. That is for sure. So anyway, have a great day, and look forward to talking again soon. We'll see you then.